Hey everybody, so welcome back. This is a virtual lab for you, a video lab, dealing with polarity. So remember, basic things with polarity, like mixes with like. So polar substances mix with other polar substances, nonpolar mixes with nonpolar. Polar and nonpolar don't mix, okay? So the point of the lab is to see examples of this, to see actual examples of this happening. You also want to keep in mind your basic intermolecular forces, okay? Dispersion forces, or London forces, occur between nonpolar molecules. That's how they are attracted. Dipole attraction occurs between things that are polar, but that are weakly polar, and hydrogen bonding occurs between things that are very polar, like water. Okay. Now, in the first part of the lab, we're looking at the flow rate of water, hexane, and ethylene glycol. Okay. So here's water. Okay. And we know that it's polar based on the electronegativity difference in the bond and on the shape of the molecule. Okay, oxygen is negative, and the hydrogens are positive. Okay. Sorry. So water is polar. Intermolecular forces, water is attracted to itself through hydrogen bonding. Okay. Hexane is what's called a hydrocarbon. It's made of carbon and hydrogen. So we have CC bonds and CH bonds, both of which are nonpolar. Okay, and here's your Lewis dot structure. Okay, the shape would be tetrahedral around each carbon, which in 3 dimensions kind of gives you this zigzag shape of carbons surrounded by hydrogens. But the thing is, this molecule has no polar bonds in it. Okay, so what sort of force should it be attracted by? Answer that now. So the type of force that would attract one hexane to another, maybe, are dispersion forces. Okay, hexane is nonpolar, so molecules of hexane are attracted through dispersion forces. Okay. Ethylene glycol, which is the active ingredient in antifreeze. It's what keeps your car engine from freezing in the wintertime. Also helps to cool it when it's hot. So in this molecule, which you see pictured, here's the Lewis dot structure, there are polar and nonpolar bonds. Okay. You also see a dipole, a polar bond here, O to H. Okay. And then here's one here. This is actually, the oxygen to carbon ends up being polar, as is this oxygen to carbon, which, by the way this is drawn, the junction here where the 4 lines come together, that's a carbon. Down here, also a carbon. That's a way of depicting molecules, which if you take organic chemistry, you'll learn more about that. Okay. And then here's an oxygen and a hydrogen, also polar. Okay. The question, is this molecule polar, and how would molecules of it be attracted to each other? So first question, is this polar? Answer that now. So this molecule is actually nonpolar. Okay. If you're like, well, how is that? If you look at each bond, each polar bond in this molecule, they're opposite of each other. This polar bond is opposite of this one. They're at a 180-degree angle. This bond here is opposite of this bond. So every polar bond in this molecule is actually at a 180-degree angle to one of the other polar bonds. So this molecule behaves in a nonpolar way. Dispersion forces are how it's attracted. Okay, so for the video, for the lab, okay, polar substances like water, because the attraction between the molecules, typically we're going to see a higher flow rate. You want to see in the data if that's what we see. Okay, in this next part of the lab, you'll see a test tube with a water layer and a hexane layer. Water on the bottom, hexane on the top, because hexane is a bit less dense than water. Okay, and then in the test tube, there are little hole punches of paper, some of which have the paper exposed. The other side is covered with graphite from a pencil. Okay, so here's a diagram of graphite. Okay. Graphite is layers of carbon atoms stacked on top of one another, where you have chemical bonds mostly horizontally through these layers of carbon atoms. Okay. The carbon-to-carbon bond, of course, is nonpolar. Okay. So what you want to think about right now, graphite, is it polar or nonpolar? Okay, so graphite is nonpolar. It contains all nonpolar bonds, and dispersion forces are what would attract graphite to other nonpolar substances. Okay, so another question you want to answer right now, will the graphite be attracted to hexane or to water? Remember, hexane is nonpolar and water is polar. Okay, so the graphite should be attracted to the hexane. We'll see if we see that in the video. Cellulose is the other side of the little hole punch. Cellulose is paper. That's what paper is made from. Okay, so the bonds in cellulose are polar and nonpolar. Here's a diagram of cellulose. The polar bonds are the O to H bonds here, and the O connecting to each of these carbons. Again, this is drawn where each junction of lines is a carbon atom. Okay, so cellulose, polar or nonpolar? Okay, so the molecule cellulose is polar because of the OH bonds and the CO bonds, and because there are dipoles that are not opposite of one another. Okay, so what we should see here is the paper should be attracted more to the water than to the hexane. Okay, and cellulose is attracted to water through hydrogen bonding. Okay, so take a look at the video now for this part of the lab and answer the questions. Okay, in this next part, you're going to see a stream of water and hexane coming out of a burette. And I'm going to put a charged balloon, a statically charged balloon, next to the stream of each substance. Okay. Now what happens, statically charged objects, like a static balloon, interact with other charged objects. Remember that a polar molecule is a charged object. It is a positive and a negative charge. Okay, so answer this right now. Which should be more affected by the balloon, water or hexane? If you said water, that's correct, because water is polar. It should be more affected by the balloon. The hexane, not as much. So take a look at this in the lab video. Okay, final part here. You're going to look at regular sand and magic sand. Magic sand you can buy in stores. It's usually blue in color. You can put it in water, and it does crazy things. Okay, magic sand is normal sand coated in trimethylhydroxysilane. You don't need to know that. It's a big name. Again, if you ever take organic chemistry, you'll learn how to name that. It's kind of crazy. Okay. So here's what happens with magic sand, the toy, right? It's normal sand coated in this rubber. This is a form of rubber, okay? You have CH3 portions of the molecule that are then going to be exposed to the environment, in the case of the lab, exposed to water, okay? So CH3 is nonpolar, okay? So the magic sand, will it interact with water? Answer that now. Again, the CH is nonpolar. Okay, so methyl groups, these CH3 things, are nonpolar, and that's the part of magic sand that kind of sticks out into the environment. They should not be attracted to water, so there will be no attraction between the magic sand and the water. And you want to see if that's what you witness in the video. Okay. Yeah, unfortunately, you're not actually doing the lab, but if you have magic sand, you can go ahead and play with it, right? It's good times. Now, the other thing here, what about regular sand? In the video, you're going to see normal sand mixed with water, okay? Normal sand is silicon and oxygen, okay? Take a moment now. Silicon and oxygen, is that bond polar or nonpolar? So that bond is extremely polar. It's almost ionic, not quite, but almost. So normal sand, silicon dioxide, will be attracted to water through hydrogen bonding. Why does sand get wet? That's why, okay? So take a look at the video for this section and see what you see.